So summarizing what we've talked about up until now, when we're talking about descriptive statistics, we're simply talking about statistics that describe the sample within your study and specifically try to summarize large amounts of raw data into meaningful information that can be communicated in a small number of values. And we kind of talked about that what we're really hoping for is that we have a normal distribution, so bell-shaped with no major outliers, and that because we have that normal distribution of a continuous variable, and again, a continuous variable is a variable that has both magnitude and equal intervals, that using that normal distribution, that continuous variable, we can communicate a lot of information in just two numbers. The measure of central tendency, which in this case we're hoping to use mean, which is the mathematical average or center point of that bell-shaped distribution, and variability, which is standard deviation. And that standard deviation tells us how much variance around that midpoint exists. So just kind of keep that in mind, that though that's what we're hoping to focus on, if that distribution is not normally distributed, there's a couple of things we can do. We can definitely look at the possibility of removing outliers and see if that fixes the problem. Or we may be stuck in a situation where we really can't use mean and standard deviation. We may have to use the median and the exclusive range. And again, remember the median is we simply put every single score from lowest to highest in order and find the center point. If it is an odd number of data points, it'll simply be the center number. If it's even, it'll be the two center numbers basically added together and divided by 2. So the average of the two center numbers on an even distribution. And again, that's to calculate the median. Exclusive range is just your highest score minus your lowest score. So that just kind of tells you where your endpoints are. Now again, you'll notice that doesn't give us as much information, and we can't make as many inferences from knowing mean, median, and exclusive range compared to the information we can gather if we have a mean, the mathematical average, and a standard deviation. But again, we can only do that if we have that normal distribution. And we finally briefly talked about mode, which is simply the number that is the most often responded, and the fact that that can be more than one number if there's a tie. And all that really gives us information about is just what was the most common response. It doesn't even tell us about variability. And normally the only time we would actually report a mode is if we had truly categorical data. Data that the numbers simply are labels for categories. They don't have magnitude, they don't have equal interval. So if we have that normal distribution and we have that mean and standard deviation, why that's so important is that we can gather a lot of information from those two numbers. Assuming we have a normal distribution, at that point, the mean tells us that basically half of the scores are above the mean and half of the scores are below the mean. The mean is the center point of that distribution and also the center where the most responses were. Most people are going to fall in right around the mean. And as we get further and further away from the mean, we should see less and less respondents that scored those numbers, whether they're higher than the mean or lower than the mean. So the standard deviation is the value that shows the relationship that individual scores have to the mean of that sample. So if the scores are normally distributed, that standard deviation also gives us a lot of information. If it is normal distribution, we know, for instance, that on average, about 68% of the scores fall within one standard deviation of the mean, either plus or minus. And about 95% of scores would fall within two standard deviations of the mean. So again, when I tell you, for instance, that something it's on a 0 to 10 scale with a mean of 7 and a standard deviation of 2, that gives you a lot of information, assuming it's a normal distribution. I don't need to give you all 100 scores. You now know what the midpoint is. You know the likelihood of someone getting above or below it, whether it's one standard deviation or two standard deviations above or below that mean. Now, this is, of course, a perfect normal distribution. And we already talked about the fact that a lot of times we're getting distributions that are relatively normal. We can use these statistics with it. They're going to be relatively accurate, but there may be some variance depending on the size of the sample. And again, the 68% and 95% is not written in stone. It's approximately 68%. In general, most normal distributions, about 68% of the scores will fall within one standard deviation of the mean. And again, approximately 95% of scores in most normally distributed samples will fall within 2 standard deviations of that mean. Now again, I would encourage you to review the calculation of mean. And again, the calculation of mean is simply every single score added up and divided by the number of scores. You have 22 scores, you add all 22 together, and then you divide that by 22. You have 10 scores, you add all 10 scores together and divide that by 10. You have 5,000 scores, you add all 5,000 together and you divide by 5,000. Now, for a standard deviation, I again encourage you to go through the slides that preceded this one. We actually see that it's a little more complex of an equation, and we actually need to calculate the mean prior to our ability to calculate the actual standard deviation. And I would ask you to go through those samples and make sure you understand that as well. A reminder on the test, there will be at the end of the test a stat sheet, which basically is going to have a couple of equations. One of those equations is going to be the mean, one of those equations is going to be the standard deviation. So you don't need to memorize the equations, but you do need to make sure you understand those equations and you know how to use them. There will be a decent number of questions on the test using those two equations. So this is just a kind of a more detailed chart, and this is actually a specific type of measure, and this is scores on the Wechsler Adult Intelligence Scale, commonly called an IQ score, though most people that research cognitive ability no longer use the term IQ. What they usually use is either G, or they'll simply call it an intelligence scale. And the intelligence scale, when the Wechsler has been given out to tens of thousands of people, probably hundreds of thousands of people at this point, and they know for fairly solid evidence that it is a normally distributed distribution, and it's centered on the score of 100. In other words, the test is designed that 100 is the mean point. And again, knowing what we know, that 68% of people score within 1 standard deviation, and the standard deviation on this test is actually 15. That means that about 68% of people fall somewhere between an 85 to 115 on this scale, with 100 being the mean. So if you randomly grabbed 100 people from all walks of life and gave them the Wechsler IQ test, or G test, or intelligence test, you would find that on average, if you calculated the mean should be very close, if not actually on 100. And if you calculated the standard deviation, you'd find that the standard deviation would be very close to 15. At which point, that also tells you that in that sample of people that you gathered, that about 68% are going to fall within 1 standard deviation of that mean. Now, 34% of them are going to be below the mean, and 34% are going to be above the mean. And again, if we go to 2 standard deviations, we're going to capture about 95% of respondents. So out of any 100 people, 95 of those 100 people are going to fall somewhere between an IQ of 70 and an IQ of 130. And again, we can see that this is smaller groups. There's only 14% of the people that fall between 115 and 130, and about only 14% of the people fall between a 70 and 85. Now, as we move out to 3 standard deviation units, you're also going to notice it's now about 2% increase. So most people, there's only about 4 or 5% of the entire population that falls into this range of either 30 to 145 or 70 to 55. And finally, less than 0.1% are going to score over a 145 or a 55, which means, again, if I have a sample of 100, there's only about a 1 in 10 chance that I'm going to have anyone in that sample of 100 score above a 145 or a 55. I need a pretty large sample to expect those kind of numbers. Now, it doesn't mean I might not get a few. There's always outliers. And that's, again, a reminder that we rarely are getting perfect normal distributions. But this is an example of a commonly used measure that has been found to be very reliably a normal distribution in most samples. So again, when we're talking about distributions and central tendency, what we're really looking at, again, is an average value, whether that's the mean, the median, or the mode. Now, moving beyond just descriptive statistics, generally what we're really interested in is comparing groups. And that's one of the reasons we want to be very careful to make sure that if we're comparing multiple groups on a variable, a continuous variable, that those variables have similar distributions. So for instance, if I have 3 groups, group A, B, and C, and I find that the mean of the first group is a 10, the mean of the second group is a 20, and the mean of the third group is a 30, that I actually am reliably able to say that one group differs compared to the other. Now notice that there is very little overlap between that first group and that second group, or third group, the white distribution and the orange distribution. But also notice that though the middle group, the yellow distribution, B, is different than the other two groups, there is some overlap. In other words, if I knew that you were in the second group, you might also have scores, if you scored lowly, similar to the group that is A, and if you scored fairly high, you'd have scores similar to those that scored low in group C. So there's not a perfect difference. There is some difference, and it's probably a meaningful difference. But again, I can make those comparisons because I know that the variance is fairly similar, allowing me to look at just the mean differences. Now, if our variability is different, for example, I might have three groups again, A, B, and C, and A is a normal distribution with a mean of 10. But B is also a normal distribution with a mean of 10, except it's not normal. It's actually possibly leptokurtic. And finally, C is also got a mean of 10, but it's a platykurtic distribution. Now, if all I was looking at was the means, I would say these three groups are identical. Group A, B, and C all have a mean of 10, no difference. But you can see that the mean itself is only useful to us as a comparison point if our distributions from different groups are similar in how they're distributed or they're similar in their variability. Because otherwise, if I'm just looking at the mean, I'm starting to lose information that's important. Obviously, group A, B, and C are not the same. Though the scores on average are the same, whatever I was manipulating had an effect. It just didn't move the average, it moved the distribution. So in other words, when I actually did my intervention in group B, assuming A was a control group, so A is the people I didn't do anything to, B, I did some form of intervention, and though I didn't actually move the mathematical average, I did get people to cluster closer to that average. And finally, whatever my manipulation was in group C, it actually spread out those differences. It made it into a platykurtic distribution. So again, when we're looking at differences, in order for us to be confident that we found differences between groups based on their means, we have to also be fairly confident that they are similar in distributions. Otherwise, when we summarize down to just that information of what the mathematical average was, the mean, we're losing too much information that's actually relevant. Again, the reason that we're trying to get down to mean and standard deviation, two numbers, is to be able to more easily compare large groups of data without having to actually talk about every single data point. But if we do that, we want to make sure that we're not leaving behind important pieces of information that do inform us of what's really going on in that sample. So distributions tell us more, and again, when we talked about skewness, a non-normal distribution, just like leptokurtic or platykurtic distributions, we start to run into some problems. So for instance, if we had three samples, one with a positive skew, one with a negative skew, we'd be able to talk about mean differences, but we're comparing group A, which the mean is the dead center of the population. But when we talk about the mean of the positive skew, that mean is no longer in the center point. It's been dragged to the positive. And the mean in the negative group has been dragged towards the negative or the lower scores, which means that the differences between these groups would actually be shown as smaller than we actually think they are. So again, the mean of group A is at 10. The mean of group B, the yellow group, without the outlier is probably at 5, but that outlier is probably bringing it to 7 or 8. And likewise, the mean of the negative skew group, C, if there wasn't an outlier there, would probably be at somewhere around 15. But again, that negative skew is going to drag it probably to close to 11 or 12, which means that if we compared these three groups, we would actually have to conclude there was less difference than there actually was based on a few outliers. And again, that's why we're wanting to look at this, is that we want to make sure that if we're making statements about the relationship between variables or the difference between groups, that if we're reporting just means and standard deviations, they're meaningful and that they are representing what people would expect them to represent. That the mean is the center point of the distribution. It's normally distributed, which means it's symmetrical, which means those standard deviation units also give us real information about what percentage of people scored above and below the mean and how far that variability was. So again, talking about kurtosis, which we've already kind of covered a little bit, Again, if I'm comparing what's often referred to as a mesokurtic distribution, which simply means normally distributed. Mesokurtic basically means it's the normal distribution. It's that bell-shaped distribution. But again, if I'm comparing it to both a leptokurtic or a platykurtic distribution, again, even though the means are all the same, the groups themselves are no longer the same. So we can't rely on just that measure of central tendency.